Good afternoon, everyone. Hope you had a good weekend. Today, we are going to finish up the lecture on signal integrity, and then we will start a new topic in hardware description language. I've got the next quiz, quiz 7, is posted on Blackboard and is due on next Monday by 3:55. As always, if you find any bugs or if you have any questions about it, don't hesitate to contact us. Can everyone hear me? Good. Okay, great. Okay, so last time we were talking about interconnect. We talked about how delay in integrated circuits is determined by capacitance and resistance, and delay is also what determines performance ultimately. I mentioned that you get delay from the logic gates, and you also get delay from wires. And so in the first part of the lecture, we talked about delay in capacitance and resistance in logic gates. And in this part of the lecture, we're talking about the capacitance and resistance in wires, or interconnect. Okay, so the wires are literally just wires. They're metal that runs across the surface of one of several routing layers or interconnect layers on a chip. They're above the substrate and the active layers where the transistors live. The objective is to have these wires have minimal resistance, and so in order to one way that semiconductor fabrication companies achieve that is by making the wires very thick. So if you look at them in the sort of the cross-sectional dimension, they're very thick, although when you design a chip you don't see that. You design them from the top down. So the aspect ratio is the thickness divided by the width, and most modern processes have the wires be twice as thick as they are wide. In the case of the aspect ratio, when they have the width, they're talking about the minimum width, not the actual width that you use. That's every wire has every metal layer, they're called metal layers, has a minimum width. Generally, the farther up the stack you go, the higher you go in metal layers, the minimum width becomes wider. And I think I have a picture. Yeah, so I have a picture of that here. So you can see that pretty clearly here. This is the Intel 90 nanometer stack. Transistors are at the bottom. This is a cross-sectional view, kind of like you're looking at the middle of a sandwich that you cut, and has 6 metal layers. You can see they're nice and thick, and you can also see that metal 4, going from metal 3 to metal 4, they become much wider and thicker. And then the Intel 45 nanometer stack has 8 metal layers. I don't know how many metal layers they have now in like the modern, like the 22 nanometer or 11 nanometer. I don't even know. Presumably they've continued to add metal layers. So I mentioned that resistors have resistance, capacitance, and inductance, but generally with the on-chip wires you don't worry about inductance because its effect is negligible. But it is something that you worry about when you go off-chip. So that's something that's actually relevant for like off-chip interconnects like SPI and I2C. But we're not going to talk about those in this course. We're just going to focus on resistance and capacitance for on-chip wires. We talked about how the resistance and capacitance is distributed across the entire length of the wire, and so when you model it, generally they're modeled as segments, as lumps. Although again, in this course we're going to simplify that, and we're just going to consider one lump. A lump is either an L model, pi model, or T model. And the pi model is the one that's generally used, which is where you calculate the capacitance for the wire, and you cut it in half, you divide it by 2, and you spread it across 2 capacitors. You distribute the capacitor across 2 capacitors in the model, one on either side of a resistor. And so the resistor is the resistance of the wire, and then C is the capacitance of the wire. And so each one of these capacitors in pi model is C over 2. And as I mentioned, you could have multiple lumps. So you could model a wire as having multiple pi's. and that's typical for longer wires and especially off-chip wires. But in this case, we'll just consider, the simple single lump pi model. So the wires are made out of metal. Metal is characterized in terms of its bulk resistivity, which is ohms times meters, or ohms times centimeters. Bulk resistivity it's strange. It's kind of like a one-dimensional measurement of the resistivity. It's not really useful until you convert it into an actual resistance. So the actual resistance of a wire is going to be the bulk resistivity divided by the thickness, which is why, this is why you want thick wires, because you increase the thickness and it brings down, it's in the denominator, so it brings down the resistance. And then you multiply that by length divided by width. Now, again, this is assuming that the current is being sent down the length. And so the width is also in the denominator. So if you make a wider wire, it acts to reduce the resistance. But typically, at least in my experience, I've only designed 4 chips, but this was a while ago. But I generally would always use minimum width wires, but you can make them wider. You have the option as a designer to make wider wires, and that would be useful for lowering the resistance. So, for example, if you had a really long wire, you could make it wider, or you could just use a higher metal layer, which has a wider minimum width anyway, and is also farther away from the substrate. So anyway, the resistance is rho over T times L over W, where rho is the bulk resistivity of the material, T is the thickness of the wire in the third dimension, kind of like the sort of the height of the wire, although height is usually used for the height above the substrate for the wire. And then the length times length over width. The length and width are designer, that's something the designer picks. The rho is just a property of the metal, and thickness is a property of the fabrication process. You can't change that. So rho over T is also referred to as the sheet resistance, which is R sub square, which is kind of odd, but that's rho over T. And this is nice because you want to take this term is something that would be locked in, something that comes from the company that fabricates the chip. It's not something you as a designer can control. So you basically isolate the two terms that you can't control, and you bundle them into this single term called sheet resistance. And so then if you want to find the total resistance of a wire, you can then take the sheet resistance and multiply it by the width, the length over the width. And so that's all there is to that. It's pretty simple. Generally speaking, wires these days are made out of copper. They used to be aluminum. Copper has a few other challenges that I actually wasn't aware of until I started looking into it for this class. I've never designed a chip with copper wires. I've always done aluminum wires, but apparently with copper, there's some additional design rules that you have to follow in order to avoid copper damaging the transistors. I don't know how that happens though, because like I said, the wires are separated from the transistors through the silicon dioxide layer, the glass layer. So it's kind of surprising to me that can happen. But apparently there's some considerations there, but we're not going to get into those. But the point is that copper has a lower bulk resistivity than aluminum. And so I have some examples here to calculate the sheet resistance of a wire where you're given the resistivity and the thickness. So you just you just take the resistivity and divide by the thickness to get the sheet resistance, and then the total resistance you get from multiplying the sheet resistance times the length divided by the width. You'll see on the quiz there's similar questions. So that's how you calculate the resistance. Basically, you start with the material that you make the wire out of, then you have the which gives you the the resistivity, and then you get a thickness and then a width and a height. Okay, so what about a capacitance? Well, that one's a little bit more challenging. In fact, capacitance is really challenging to calculate because it's affected by if you have something above or below the wire. Now remember that above and below the wire, immediately above and below the wire or oxide, is glass. But then on the other side of that is going to be other wires or possibly a plane. So a plane would be like the substrate, for instance. Like the substrate of the chip is ground. It's like a big chunk of conductive material that's grounded. You don't really have planes above wires, as far as I know, anyway. In an integrated circuit, I'm kind of surprised that they show it that way. Generally, if you have a plane, it would be on below, right? It would be the substrate. I don't know what would be above it, although these days now they're making 3D stacked integrated circuits where you can have a chip, and then you can literally put a DRAM on top of it. That's how they make those high bandwidth memories. And there's been some talk of doing other kind of crazy packaging stuff like that. So down the road, I think this capacitance, having to consider the capacitive effects of doing different types of packaging structures may be important. But anyway, the point is that the capacitance is determined by other conductors around the wire. So you would have to add all those up in order to get the capacitance of the wire. In this class, we're going to simplify it again, and we're only going to consider the capacitance to the ground plane, the substrate, which is calculated simply from the width and the height of the wire, above the height being how far above the wire is above the ground plane or the substrate, which would be determined by the oxide thickness, and then also the length of the wire. So length, width, height, and epsilon ox, which is the dielectric constant of the oxide. So what is the dielectric constant, by the way? We talked about that a little bit already. I didn't go into a lot of details, but basically there's this term called permittivity, and the dielectric constant is how much more permittivity you have as compared to vacuum, and that's what that epsilon ox is. So the number there for silicon dioxide is 3.7 or so. In a circuit board, they have material that goes between the layers of a circuit board, but they can't use silicon dioxide. I'm not sure why. They used to use that in like multi-chip modules, and I think they might be using them these days in these new interposers they're building. But in a circuit board, you can't put glass in a circuit board, basically. So in a circuit board, they use another type of dielectric material, or when I say dielectric material, I mean an insulator material that to separate the layers. And they have different types. They have F4, and then they have Rogers material. But anyway, the lower number, the better. So you want the dielectric constant ideally to be lower. And so in the case of silicon dioxide, it's 3.7. And in the case of a circuit board, if you have F4 material, FR4, it would be 4. But anyway, that's what that epsilon is. And it's generally for an integrated circuit, you always use silicon dioxide. So generally, that's always going to be the same. I don't think doesn't change. The height, on the other hand, though, is related to the thickness of the oxide, and they do reduce the thickness. They make the oxide layer thinner with each successive generation of a chip technology. So anyway, this is just an empirical formula, so they just kind of did a fit. Empirical means that they basically built some wires and they measured the capacitance, and then they developed this equation to basically fit the measurements that were observed. So it's basically it's right here. It's like I said, it's a function of the width, length, height, and epsilon. So basically, all you can do is plug these in. Now, this, as I mentioned, though, this does not account for capacitance to neighboring wires or to anything above the wire. This is just the capacitance to the substrate. So this is obviously, simplistic, but it gives you an idea of how, what factors affect that. Okay, so here's another example. You'll see on the quiz, I have some similar examples. The question is to estimate the delay of a full path, which would include the output of a gate and the input to the next gate that you're connected to. So you're taking a gate and you're wiring it. You're taking the output of one gate and wiring it to the input of another gate, and in between you've got a wire. So in this case, it says estimate the delay of a 10x inverter. What's 10x mean? That means it's a 10. It's an inverter that's 10 times the minimal size. So it's a big inverter. It's a driver. It's a powerful inverter, and it's driving a 2x inverter. So why would we have a big inverter? Well, it's because having a big inverter lowers the resistance, but it also increases the capacitance. Let's see. So it says that the unit size inverter has a resistance of 10 kilo ohms. So a 10x inverter would have 1/10 of that, so 1 kilo ohm or 1,000 ohms. And the input capacitance of a unit size inverter is 0.1 femtofarad. So if you're driving a 2x inverter, it would be 0.2, but you have to multiply that by 3, though, remember, because you have to drive a double size PMOS and a normal size NMOS. So that's where you get the 0.6. And then in between, you've got wire resistance of 800 ohms and wire capacitance of 200 ohms, which is divided across the two capacitors. And then to calculate the Elmore delay, remember, you're just multiplying the resistance times the capacitance, but you have to consider that you have multiple paths, resistive paths. So it would be 1,000 ohms times the first capacitor, so 1,000 ohms times 100 femtofarads, and then you have to add the next segment, which is separated by the first segment through this resistor, and then so you have to add the two resistors, 1,000 plus 800, so that would be 1,800 ohms, then multiplied by the next segment of the capacitance of the next segment, which would be 100 femtofarads plus 0.6 femtofarads. And so now you might say, wait a minute, are you telling me that all the units here just work out and you end up with seconds? Yeah, believe it or not. Remember, femto is 10 to the negative 15th power. And then pico is 10 to the negative 12th power. So you have to make sure that you keep the units consistent when you calculate these delays. So this ends up becoming the delay is 281 picoseconds. Now you might say, wait a second, doesn't the output of a gate also have capacitance, diffusion capacitance? Yeah, it does actually, but it's not. For whatever reason, I got this example from the textbook. This particular example didn't say to include any output capacitance, but that's something that I might ask you to include, on the exam or on the quiz. So just be aware of that. But in this case, it's kind of simplified. It just says that, essentially it's a 1,000 ohm driver. Okay, and then we talked about last time wire energy. So the dynamic energy, which is actually also known as power, would be capacitance times voltage squared times frequency. In this case, though, if you take the frequency out, if you take capacitance and just multiply it by voltage squared, you're going to get how much energy is required per bit or per bit flip. And so you can either multiply that by frequency to get the power, or you can keep it, in terms of energy per bit. And then in this case, it's they have they ask for energy per unit length. You can scale it by a billion to get milliwatts per gigabit per second per millimeter. In this case, per millimeter, because one of the capacitance terms is picofarad per millimeter. But the point of this is that the energy is capacitance times voltage squared, and then if you multiply that by switching rate, you can then convert that to a power. Okay, then crosstalk is when you have capacitive coupling between adjacent wires, and one wire switches state, from 0 to 1, 1 to 0, and it induces a voltage swing in the other wire. So the wire doing the switching is called the aggressor, and the other wire is the victim. And this is actually this is a big concern. I mean, this is where this is one of the primary sources of noise on a chip, on wires, is this crosstalk. And so the idea is that if you have a wire and it's next to a ground plane and you've got a really good ground connection, then you're probably not going to be able to change the voltage of the ground plane. But when you have two wires together and one switches, it's depending on how hard the victim wire is being driven by its own driver, you can get a significant swing in that other wire just through capacitive coupling. But like I said, it depends on how strongly you're driving the other wire. So in other words, what I'm saying is that if you have a wire that's connected to a big gate, a big meaning its width, it has a wide gate, it's a giant gate, then it's going to be harder to get noise on there, right? But if you have a wire that's either undriven for whatever reason, it might be tri-stated or whatever, you might have an undriven wire, or you can have a wire that's connected to a weak driver, then it's going to be more susceptible to this crosstalk noise from neighboring wires. So if you have so this is a picture of what I was explaining. So if you have an aggressor, it's got a capacitive coupling to a victim. The victim has its own capacitance to ground. And so you can calculate the voltage difference that's caused by from this, assuming the victim is undriven. It's just the capacitive coupling, which is C adjacent. So what the effective capacitor is between the two wires. Now you might say, well, how do you calculate that? Well, that would depend on how long the wires are, how close the wires are. It would be you'd have to use an equation similar to what we did back when we calculated the ground capacitance for a wire. It depends on the shape of the two wires and how close they are. So this is something that's in your layout, and the value of this is given when you extract. So you go through a process called layout extraction, where you draw your design and then you do extraction, which extracts the parasitic capacitance out, and this is considered a parasitic capacitance. Anyway, so you've got this capacitor. Oh, and by the way, when you do the extraction, what you end up with is a big schematic that includes not only the transistors that you intended to make through your design, but also all these, these passive elements, with these parasitic elements, these capacitors and resistors. But anyway, yeah, so it's basically just capacitance of the adjacent wire divided by its ground capacitance plus the coupling capacitance, C adjacent, and then you would multiply that by the voltage swing in the aggressor, and that's how much voltage swing you'd see in the victim. This is major, obviously. This is a big deal if the victim is not being driven. If you switch the aggressor here, you're going to get a pretty substantial swing potentially in the victim. However, if the victim is being driven, if someone's already setting the victim to 1 or 0, depending on how strongly you're setting that, and when I say strongly, I mean what the effective resistance is between the victim and its power or ground, depending on whether it's being pulled up or pulled down, then the voltage swing may not be that bad. So in order to calculate that, it's you basically have to calculate this K value, which is essentially a ratio of how strong the aggressor is versus the victim. And so so K is this tau sub-aggressor divided by tau sub-victim. So it's the ratio of aggressor strength to victim strength. The aggressor strength is going to be the resistance multiplied by the ground capacitance of the aggressor plus the coupling capacitance. And then the tau sub-victim is the resistance of the victim line multiplied by the victim's capacitance, the victim's ground capacitance plus the times the, or plus the, sorry, the coupling capacitance. So that's going to give your K value. And then you would just use the previous equation that we used for the non-driven victim, but you'd scale it by 1 over 1 plus K. And so you end up with, essentially a model that looks like this, where you've got the aggressor, which is switching from, in this case, 0 to 1, and then the victim is, being actively driven down. In this case, it's being pulled down to 0. I always get confused by these symbols. So the ground is the arrow pointing down. The VDD is a little T shape. But I always get those mixed when I'm drawing these circuit diagrams. Okay, so there's so it's not really that hard to calculate, but the idea is that you're gonna have less noise in wires that are harder driven. So that gives you another incentive for not using minimum size gates, especially if they're if they're connected to long wires. Okay, and then finally, crosstalk delay. So I want to clarify this. I did not explain this correctly in the last lecture, so I want to clarify this. So I think in the last lecture I implied that that this had to do with crosstalk, and I didn't mean to do that. This is just delay. If you have two wires that are next to one another, you have crosstalk, but you also have additional delay, not necessarily noise, but delay, that is caused when you have two wires that are switching opposite of one another, or switching, if you have one switching, if you have one that's say A is at 1 and B is at 1, and then B goes down to 0, right? So you would have this this Miller effect, which is basically where the capacitance of the wire is, you get additional capacitance in the wire. So you not only get the ground capacitance, but you get this adjacent capacitance. So basically, if you go back, I had a slide at the beginning here that showed this, right? So I mentioned that we're not considering this top plane. We have this ground capacitance, and then there's these neighboring capacitance. So technically, we actually are considering these neighboring wires here, in this case with Miller effect, with this Miller effect. So we're adding additional capacitance to these neighboring wires. But the capacitance is even worse if you're switching opposite. So if A is switching from 0 to 1 and B is switching from 1 to 0, then the capacitance seen on either one of these guys, the additional capacitance, is actually 2 times the adjacency capacitance, the coupling capacitance, right? So basically what I'm saying is that this Miller effect is additional capacitance that you would use when calculating the delay of a wire. That comes from crosstalk, but it's not noise from crosstalk. It's just additional delay from crosstalk. And then if both wires are switching together, then you don't have any additional capacitance from the crosstalk, right? So if A and B are both transitioning from 0 to 1 or 1 to 0, then the C sub adjacent does not factor in at all. You just have the ground capacitance. So I'm sorry, I really screwed up my explanation of that last lecture, but this is just, again, this is just additional capacitance for calculating delay coming from adjacent wires. Okay, so yeah, so this is a neat figure that was in the book. It just basically shows that if you have an undriven wire, basically you can, if you switch the aggressor from 0 to 1 volts, you could see up to a 0.5 volt swing in a victim wire if it's undriven, but if it's driven with a half size and driver, it's not affected as much. And obviously a double size driver would be affected very little. Okay, so last topic is noise. So we talked about crosstalk, which causes noise. The noise is where the signal is degraded between a driver and a receiver. So you're always going to have noise. The question is, how much can you tolerate? So you have this idea of a noise margin. So this part is a little confusing. So I'm going to try to explain this carefully. So when you have a gate, if you show, and I'm not sure if I showed a figure like, so this is a buffer basically. This is kind of like an inverter, but it doesn't invert. So you have this this plot. You have two plots here. If you look at the one on the left, the horizontal axis is the voltage of A, the input, and the vertical axis is the voltage of Y, the output. So we're plotting the input to the output voltage. Actually, this is the same setup we use actually when I was talking about the different the different operating modes of the pull up and the pull down transistors in an inverter. So this is the voltage response of a gate, right? So you increase the A from 0, and at some point, ideally once you hit halfway. So if this is a 1 volt process, ideally once you hit half a volt, on the input, then the output will switch, right, up from 0 to 1. So when the input goes from 0 to 1, the output switches from 0 to 1, because again, this is a buffer, not an inverter. If it was an inverter, it would be the opposite. But ideally, you'd have this nice square-shaped, trace. You get to the input would reach a certain voltage, and then it would cause the output to change, instantaneously, right? So you'd have this nice discrete plot. But in reality, we know from actually having walked through this with the inverter, that it doesn't actually look like that. It looks more like this S-type shape, where as you increase the input voltage, you kind of see this gentle rise in the output voltage, where you're in the linear mode of the I always forget. You're in the linear mode of is it the pull down? No, the pull up transistors, right? You start to get in the linear mode. Obviously it's in cutoff. You can see that, it's in cutoff for a while, and then you see the line kind of stays at 0 until at some point you start to linearly increase the voltage. This is when the PMOSs would be in linear mode. Well, actually that's not, wait a minute, that would be true for an inverter, but this is a buffer. So that's a bad analogy, but you get the idea. The output sort of goes up linearly at a certain point, and then it jumps up real fast when both sides go into saturation mode, and then you get this kind of linear roll off, and then finally cut off, right? So you get an S-shaped curve basically. And so there's these unity gain points, which is the point at which you go from basically linear to saturation mode. You go from a very gentle rise of the output voltage to a very steep rise. And so that happens when the slope is 1. So the slope is less than 1 here, and then it's greater than 1 here, but it's going to equal 1 here, right? Same thing up here, right? So these unity gain points are simply when the slope is 1 on the when the output voltage slope is 1 relative to the input voltage, right? And that happens at 2 points. It happens when you're about to basically once you go into saturation mode and once you exit saturation mode, basically. Okay, so I think that's pretty, I think that hopefully that's pretty clear. Now, what is important about this? Well, the important thing is that the unity gain point, if you look at the voltage on the input versus the voltage of the output, where the unity gain point is, they're different. The input voltage is going to be higher, right? Why? Well, because the slope was less than 1, right? I mean, because basically you were increasing the input, quite a bit and getting very little difference in your output, right? Again, because the slope was less than 1 during that interval. So you're going to have, VIL, which represents the voltage of the input low, and then you're going to have voltage output low. So what VIL represents is the highest input voltage you want to be at before, the highest input voltage that would be considered a 0, essentially in the eyes of the input of the gate, right? So the gate will assume that anything below VIL is a 0 input, and likewise anything above VIH will be considered a 1, right? So this is basically just taking a voltage and converting it to binary, essentially all it is. But this is for the input. Now the output of the gate will kind of behaves the same way, where there is a voltage on the output that the user of the gate should consider 0, anything below that to be a 0, and that's the VOL. And same thing with VIL. Anything above VIL should be considered a 1, so on the output. So basically the question is, what does a gate consider as, what voltage constitutes a 0 and 1? Well, the answer is it depends on if it's the input of the gate or the output of the gate. You might say, well, why is that? Well, that's because these unity gain points. And then you might say, well, why is that? Well, that's because of the operating regions of the transistors, the point at which they go from linear mode to saturation mode. So that's it. You've got different thresholds basically for what's a 0 and a 1 for input and output. Now you might say, well, wait a second. What happens if the voltage is between? What if the input voltage to the gate is between VIL and VIH? If that's the case, that is the forbidden zone. You don't want that because, for one, you're going to be in saturation mode on the pull up and pull down, which means you're going to be wasting power. But also, it's kind of, it'll give you an output that's also in the forbidden zone, right? So you won't know whether the gate's giving you a 0 or 1 because the gate won't know if you're giving it a 0 or 1. As input. So that's the problem. You got the forbidden zone. Now notice that the forbidden zone for the inputs though is pretty small, but the forbidden zone for the outputs is pretty big. And you can take advantage of that because the difference between the input and the outputs thresholds is the noise margin. So if you take the, for example, VIL and you subtract VOL, that gives you the NML, which is the noise margin low. So basically what that means is because there's a difference between what constitutes a 0 on the input versus that output, that means that you can tolerate noise on the wires between the gate. So if you have one gate driving another, you can tolerate some noise there as long as the noise is less than the noise margin, as long as it's within the difference between the output and the input thresholds for 0, and likewise for 1, right? So in this case, the noise margin high is VOH minus VIH, right? Output high versus input high, and likewise the noise margin low is the VIL minus the VOL. So obviously you have to swap those when you're subtracting, right? Yeah, so those are written out right here. Noise margin high is VOH minus VIH. Noise margin low is VIL minus VOL. And that's how much noise you can have affecting the wire. Now you might say, well, wait a second. Are you talking just about crosstalk? No, there are other sources of noise as well. There's crosstalk, that's a major one. But there's also power supply noise. When these transistors switch, they actually, the voltage supply, the VDD, is not stable. It's noisy. It's got like noise on it. It's like static. Because the transistors, when they switch and both the pull up and pull down go into saturation mode, there's a current draw on the power supply rail, and every time that happens, the voltage of the power supply dips a little bit during that transition period. So you got a lot of noise on analog circuits. I'm sorry, on digital circuits, which is why if you have an analog circuit in that chip as well, like if you have a mixed signal chip, you have to be careful that you keep them separated, because the analog circuits can't tolerate noise like digital circuits can. So if you have a mixed signal chip, which actually all of you do in your phones, the way they separate them is through wells. Remember the well is that, remember that diffusion area that changes the substrate material for the PMOS transistor. They use that. They use wells to literally demarcate analog parts of the chip and digital parts of the chip. And the well presumably keeps some of the noise out. And of course, you have to use separate power supplies too, as well. Anyway, so that's just that's your noise margin. So that's all we've got for that. Just enough to give you kind of a taste of the sort of issues you have to deal with when trying to improve performance on these chips. Okay, so now I'm going to switch topics to the next topic, which is going to be hardware description language. Okay, hopefully you can see the slides there. I just switched slides. You should see a slide that says SystemVerilog and finite state machines. If not, let me know. Okay, so this is a topic that I also cover in my CSCE 611 course. My understanding is that none of you have taken that yet. You will take it next year, and you'll see this material again when you take 611. You might be wondering, why cover it in two different courses? Well, what happened is in 611, the content of that course has been growing over the past few years pretty quickly, and the reason is because the course was originally just a kind of a lab course where students would just work in the lab, but we've been incorporating an increasing amount of conceptual material into the class too, for several reasons. One is to give everyone some more background information, because we don't, as you know, we don't offer a lot of hardware courses in our department, and so I try to make it up by introducing a lot of hardware concepts like I am in this class, but I have even more concepts that I introduced in 611. And also I have to review a lot of stuff from 211, because I discovered that you guys don't remember a lot of stuff from 211 and 212 because you take it 2 years before you take 611. So there's a lot of time, and you don't use it either. I mean, that's the other big deal. I mean, it's not like, obviously you learn to program your freshman year and you're programming in your senior year, and you don't forget it because you program pretty much all the way through. But there's this kind of interruption between your sophomore year and your senior year, and so you forget a lot of stuff. But that's one reason. The other reason is that project courses where the students work in groups always result in one member of the group contributing more, and that's unavoidable. I mean, it's impossible for you to have a group where everyone contributes the same amount, because everyone has different personalities, and if you have a more dominant personality and you're in a group, you're going to probably end up doing more work than the other people in the group, and that's just unfortunately unavoidable. And so in order to make the class fair, I put a lot of stuff in, kind of individual quizzes and exams and stuff. So I've been adding a lot of stuff to 611. And the one of the impacts of that is that I found it very difficult to get this hardware description language topic across. I'm having a hard time teaching it in just one semester, or just part of one semester. So I have decided to introduce it here in 317. And also I want to focus on finite state machines a little bit more too than I normally focus in 611 on that, because we don't actually use those in our 611 project. So I'm going to introduce this material now. You'll see it again in 611, but hopefully, having seen it once already, this will improve the productivity in 611, and you guys will be a little bit more prepared. So that's kind of the background. That's why this might seem redundant, but I think this is going to be a good approach. Okay, so first of all, what is hardware description language? What am I even talking about? How do you design a chip? How do you design a CPU? You guys probably, I mentioned layout already. I talked about doing basically drawing shapes that represent the different layers, the diffusion areas and the polysilicon and the wires, right? Obviously, you guys have also designed some digital circuits in 211. You guys wired together 7400 series chips. You've designed circuits on paper in your electrical engineering classes. You've designed Boolean logic circuits in 211, hopefully. You've written out Boolean logic algebra in 211. So you guys have done some hardware design, right? You guys done it. But the problem is that, modern chips have billions of transistors on them. And obviously nothing that you've done so far is applicable to these large scale designs. So how do you do a large scale design? Well, you use hardware description language. And believe it or not, all this is a high level language like, Java, for instance, but you compile it into hardware. So you literally write code that becomes hardware. Now the whole trick here, the reason why this is applicable for large scale designs, is that you can write a little bit of code and it'll generate a lot of gates. You get a lot of bang for your buck. And also the code is testable, it's reusable. In some cases it's self-documenting, or if it's not self-documenting, you can document it, add comments. Also because it's code, you can check it into version control systems and repositories. There's a lot of advantages to designing hardware using a high-level programming language. The downside is that there is some downsides. Yeah, thank you, Charles. The downside, although VHDL is designed specifically to be self-documenting in syntax of the language. But yeah, I see what you're saying. But anyway, so there's a lot of advantages, but there are also disadvantages. The disadvantage is you can design some HDL code and it may work perfectly in a simulator, but when you go to generate hardware, which is a process called synthesis, as opposed to compile, it's not called compiling, it's called synthesizing. When you synthesize the hardware, you find out all of a sudden that you have a long path, right? Path being you got a lot of logic gates in series with a lot of wires. Because why a lot of wires? Because you've got a fan out. You got a lot of fan out in your code, and that fan out has a lot of capacitance, and your design is slow. And you're like, well, I don't understand. I wrote the code, I ran the code, it works. Why is it that the hardware that this code generates sucks? And unfortunately, there is no solution to that. There is a fundamental difference in abstraction that it's very difficult to look at your hardware description code and figure out why the circuit it generates is slow. That's the downside. Now there's some ad hoc ways, you can look at it and say, well, I can kind of imagine what kind of circuit this would generate, and yeah, it would be there'd be a lot of gates in parallel. I'm doing 5 add operations in between one clock cycle, so yeah, it's probably pretty slow. But there's no direct way to actually measure that or to understand that. There's no way to reason about that in your code, unfortunately. So that's the downside, is that it's a little abstract, and sometimes it's hard to kind of visualize what hardware would correspond to the code that you write. That's the downside. And I still, I struggle with that. Everyone that does this struggles with that. Okay, so anyway, yeah, so that's what an HDL is. There's 2 main HDLs. There's the 2 most popular are VHDL and Verilog. VHDL is VISIC HDL, and VISIC is an acronym in and of itself that stands for Very High Speed Integrated Circuit. Verilog, or SystemVerilog as it's known by its latest standards, is another one. VHDL is based on Pascal. You guys don't learn Pascal, so if you looked at VHDL code, it would look very foreign to you because it's very verbose and it's designed to be self-documenting, as I mentioned. Whereas Verilog looks a little bit closer to Java or C, but I think it actually resembles MATLAB code. It's very similar to MATLAB, and maybe kind of similar to Python in some ways. So you're more familiar. You're going to be more comfortable with Verilog. So that's why I teach it in this class and in 611. I used to teach VHDL, by the way. I switched about 5 years ago or so. VHDL was designed by the government. Verilog was designed by private industry. They're both very commonly used. There's a lot of smaller HDLs that have been proposed, like Blue Spec, for instance. There's another one called Chisel, but they all come and go. None of them ever last. VHDL and Verilog have been around since the early 80s, and they're still wildly popular. All the ones that have come around claiming to replace them have all failed. So anyway, so I mentioned that there's simulation, which is where you write your code and you test it, you simulate it as if it's a, you simulate, it's like simulating a logic circuit like you do with SPICE, sort of, except SPICE is a circuit simulator, not a logic simulator. So when you simulate HDL code, it's with a logic simulator where everything is binary as opposed to analog voltage values. And then synthesis, as I mentioned, is when you kind of compile the code and convert the high-level code to logic gates and wires, basically to a schematic, a hardware schematic. Yeah, Charles has the SystemVerilog spec. Both of these are IEEE standards. Actually raises a question. Other programming languages aren't IEEE standards, are they? Well, there's ANSI. There's an ANSI standard, but I don't know about IEEE. I don't know if there's an IEEE standard for C++. I don't think so. Yeah, there's ISO, and yeah, it's kind of weird that yeah. So anyway, but yeah, before we get into too deep in the weeds here, so that's we're going to use Verilog, but once you know one, you can learn the other. Okay, so there's a couple things about HDL code that is common amongst all HDL codes. Oh, by the way, HDL stands for Hardware Description Language. Some people refer to it as RTL code, which stands for Register Transfer Language. They're exactly the same thing. I think at some point someone tried to claim that they were different, but in reality, they're synonymous. So there's two different styles of HDL code. Style is like if you look at code, you can kind of identify what style it's following based on what's in the code. There's behavioral, which describes what a module does. So basically, behavioral is Boolean logic, or sometimes arithmetic. Although usually you don't actually rely on the language to do arithmetic. Usually you build like IP that does the arithmetic, other submodules. But like you can build like little multiplexers, like which is like a little conditional statement, and also RAM. Like if you have a memory and you want to say, well, I have a memory and it has 4 ports, and it has a 1-cycle read latency. That's basically behavioral description. And then there's structural descriptions, which is where you essentially describe a interconnection of modules like a schematic using Verilog, kind of like literally just describing a graph of instance components and how they're wired together. You don't have to have those in separate files. You can mix and match them. But generally speaking, when you look at HDL, I'll tell you that most HDL is structural. 99% of it is structural, because it turns out that the behavioral code is usually only at the bottom level, and everything as you build up from the bottom up is all structural. So you end up with some simple components that are behavioral, like a multiplexer or a register or a RAM, but then you take those components and you connect them using structural code up and up and up and up the hierarchy until you end up with a really complex design. But like if you randomly went to GitHub and opened any Verilog code randomly, there would be, I would guess there'd be a 99% chance that code would just be structural. You'd be looking at basically a schematic, because the behavioral code is kind of reserved for the primitives, the low-level components, because everything is built on top of those. Yeah, Charles is right. There's if you say RTL, you sound cool. Yeah, so Philip mentions the structural Verilog is like plumbing around submodules. That's the difference. So we will be writing both behavioral and structural. I'm not going to have you do any simulation in this class because we're going to do a lot of that in 611. I just want to introduce you to the syntax of the language and how it works. So we're just going to be covering the conceptual parts, and hopefully this will be a good introduction for the 611 stuff. I'll probably spend the rest of the semester on this because there's a lot to talk about. Yeah, so I'm gonna stop here because I want you guys to have an opportunity to go look at quiz 7. The quiz 7 is on Interconnect, and obviously we've switched topics now, so the sooner you look at that while the Interconnect material is fresh in your mind, the better. And then I'll see you on Wednesday. So thank you, everyone.